Hi class, welcome to our lecture on chapter 4, which is going to be global climate, and you can't see it there, global climate and biomes. There we go. Oops, sorry, skipped a slide. So as always, we're starting off with our case study. And our case study for chapter 4 is about wine growing, specifically in different parts of the world. And the reason they picked wine is because wine requires a very narrow range of conditions, which are listed there: mild, wet winters, hot, dry summers. Not something you need to know, but the idea is that with climate is very specific to an area. Wine can be grown in a specific area because of the climate that's there. If the climate matches what is good for not just wine, but any kind of plant growth, then that makes for a good area in order to grow those highly specific crops. Things like corn and some of these other staple crops that we're used to hearing about can be grown in a variety of conditions because they're pretty well adaptive. Wine has a very narrow range of conditions, so it's important that the climate in the regions where wine is being grown stays fairly consistent. Now, obviously, when we talk about climate change, we start to worry about whether or not wine and other plant species would be able to adapt. And if they can't adapt, then it's going to be tough to survive when we talk about some invasive species coming in. Now, just because weather patterns change or weather itself changes, that doesn't necessarily mean climate is changing, because we do have a big difference between weather and climate. Climate is long term. It's the average weather, the average conditions, what would allow, let's say, wine to grow in a specific region. Weather is the short term, whether it's today, tomorrow, a week from now, a month from now, the day-to-day type of weather. So if a certain yearly crop of wine is spoiled because of poor weather, that's the short term. If wine itself can or can't be grown in an area, that's because of climate, which is, of course, the long term. So our first lecture in this chapter is going to be about climate and what defines climate. Now, climate is basically the result of the sun's interaction with mostly abiotic factors on Earth, specifically speaking, the water and the air. But so it all starts with discussing our atmosphere. Obviously the first place that the sun is going to pass through and the sun's energy is passing through. You don't need to know everything about the Earth's atmosphere, but you do need to know that the troposphere is our closest layer to Earth. That's the layer we exist in. And the stratosphere is the one that is right above that, because the borderline of the troposphere and the stratosphere is our ozone layer. Obviously, if we're talking about climate change and depleting ozone layer, we're going to be focusing on what's happening at the border of these two boundaries of our atmosphere. It is important to know how far up they are. So 10 miles up to the troposphere, and then about the next 20 miles up past that is our stratosphere. So you get an idea that the ozone layer is about 10 miles above the Earth. And we can see there relative temperatures as the sun is passing, as the sun's energy passes through. And you can see that we're in a fairly regular, as it gets down to the troposphere, our regular, where we are, we get into our fairly regular range of temperatures, average temperature of about 20 degrees. We see that as it rises up the troposphere, air temperature is much, much cooler, and then we reach our ozone layer, and in the stratosphere it warms slightly. So what causes climate in different areas? It's all because of unequal heating of the Earth. The Earth is not a flat plane, it is a circle, which means that the sun, which is coming in on a straight line, is going to hit it at different angles, and it's going to cause unequal heating, unequal energy distribution. So warming does not occur evenly, so that solar energy that hits different spots of the Earth is going to vary by location. So what causes the unequal heating? Well, the angle of the sun's rays in relation to the Earth, so whether or not the Earth itself is at a more planar angle or at a steeper angle to the sun at that moment in time. The amount of surface area that the sun is hitting determines how much sun is actually reflected, which we're going to call how much sun is reflected off versus how much gets absorbed, and the stuff that's there in particular areas. So whether or not more stuff will reflect off of Earth or not, which is called albedo. And next week we're going to do a lab involving albedo and calculating albedo of different variations of abiotic factors in areas. So we see here talking about angle. The equator is always known as tropical areas are always warm because the sunlight is basically striking it dead on. And since it's striking it dead on, more energy is going to be absorbed there. Now the sunlight strikes the Earth up here at an oblique angle, and since that's happening, that same amount of energy that would strike the equator in a more smaller range over here is now being spread out over a larger range. Since it's being spread out, it's clearly not going to warm this area to the point that it's going to warm this much smaller area. It's basically like trying to use a heater to heat up a small room in your house versus trying to heat up the entire house. That one room is going to get pretty warm pretty quickly, but in order to heat up the whole house, it's going to take a lot more energy once being spread out over that that larger range. Now, albedo is basically how much of the sun's rays are reflected by different things. And you can see by looking at all the natural stuff that there's different amounts of the sun's rays that can get reflected. Obviously, the big ones we're going to really focus on are things like snow and ice versus urbanized things like asphalt. Look at that number. 90% of the sun's rays are reflected by ice. Sea ice specifically, does a really good job of regulating the amount of energy that reaches Earth and gets trapped by the physical material on Earth because it does a great job of reflecting it. Well, as we lose sea ice, we're going to start to gain more energy, which is going to be responsible for causing warmer temperatures in the ocean. That's going to create a positive feedback loop where more energy in the ocean is going to lead to more melting, and more melting is going to lead to more energy reaching the ocean, and it's going to create a positive feedback loop of temperature rising in the ocean and the amount of sea ice and the amount of the sun's energy that's going to that's not going to get reflected. We see that the forest, grasslands, they don't reflect too much. They're pretty good at absorbing it. Cloud cover can be depending on the type of clouds. And then we look at asphalt. Asphalt at most only reflects about 10%. So the more we urbanize, we're seeing the more and more energy is getting held in, basically being captured in the ground itself. And all that excess energy that's getting trapped is going to lead to hotter air temperatures. We're going to see that what hotter air does in comparison to cooler air and what that means for different weather and climate patterns. So as the sun comes down, we know that it's going to hit things and it's going to cause unequal heating of different parts of the earth. Well, one of the things it's going to heat up is the air temperature. And if air is at different temperatures, it's going to circulate. So now what causes air circulation? Well, basically these four factors we have here. So density is the obvious one. Air that is warmer is less dense, it's going to rise. Air that is cooler is denser, it's going to sink. Just like warmer water versus cooler water. We'll talk about that in a little bit as well. Water vapor capacity becomes a big one when we talk about storms because as air warms and as climates become warmer, if the air is getting warmer, the air is able to hold more water. And if it's holding more water, that means that when that water is released, we're talking about larger and more violent storms. This term, adiabatic heating and cooling, is basically as this less dense air rises, it's going to eventually reach a point where it's going to get cold, as we saw in the beginning when we were talking about the troposphere being much cooler as you rise up. Well, that air is going to cool and then it's going to sink back down, it's going to condense, and once it gets closer to the surface, it's going to heat up again, and it's going to create this nice little circle of what's called adiabatic heating and cooling. Now, this has to do a lot more with pressure as well, because warmer air is going to have less pressure because it is technically rising. Since cooler air is sinking and condensing, it's going to create more pressure. And the last one is latent heat release, which has to do with when water vapor condenses into liquid water. Basically, as it rains, energy is released and air warms. You might notice this when it snows. A 20-degree day and it's snowing will feel warmer outside than a 20-degree day with no precipitation because as that water vapor is condensing into a liquid, or in the case of snow, a solid, energy is being released, so the air does actually feel warmer. Now, in terms of saturation, we're not going to worry too much, but this is a chart that we'll look at a little bit more in class. But basically, it's a chart that allows us to figure out, and if you ever had this question, it's fairly easy, basically just how a drop in temperature relates to a change in precipitation, meaning a temperature dropping by about 20 degrees Celsius would result in approximately 30 to 20 grams of precipitation falling in that area, or based on the size of the area. And that's how they are able to predict rainfall amounts and snowfall amounts. So with all of that air moving, basically doing all of those things, we get what are called Hadley cells, which are basically convection currents of air. Basically, warm air is rising. As it meets dry, cooler air higher up in the troposphere, it cools and sinks back down where it gets warmed up again, etc., etc. Well, the thing is, these patterns of rising and falling tend to happen at signature lines on our globe. The rising occurs at the equator. It's called the intertropical convergence zone. Forgot the acronym for a second. Intertropical convergence zone, which are basically where the tropics of Capricorn and the tropics of Cancer are meeting. And since those things meet at the equator, what we have is all of that warm air, because that's that concentrated area where the sun's rays are hitting, starts to rise. As it starts to rise, it cools, and the cooling doesn't fall straight down, but since it's cooling, it starts to move, and where it actually begins to fall, because it's being pressed up, is that it actually falls at 30 degrees north and 30 degrees south. Now, we said that as that air is warmer, that warmer air is that latent heat release, making air warmer as it precipitates. That's why we have tropical areas along the equator with heavy rain. The condensation of water vapor produces that latent heat release, so that air is definitely expanding and rising as that's happening. And as it cools, it falls down over 30 north and 30 south, which tend to be hot, but still fairly drier areas. Let's just move the screen very quickly. So again, the Hadley cells are convection currents between the equator, 30 north and 30 south. Since the equator sees the most intense sunlight, that's where we see the ascending branches. Now, because of this, we're also going to have these things called polar cells, and we'll see those on the next slide, which are basically the same thing, but because of the air not being so warm, we see the cool air sinking in certain places and displacing warmer air. That occurs at 60 north and south, and where the air is rising, and it sinks at the poles, because the poles obviously being the coldest spots. That's where most cold air sinks, 90 north and 90 south. The cold air is sinking there and displacing air upwards at 60 north and 60 south. We call those polar cells. The term ferrule cells is good to know, because those are basically the air cells that fall in between. Now, in a couple of slides, we'll see what those, and we can jump ahead if we want to, just so we can see. So here we see our polar cells, that cool air sinking at the North Pole because it is so warm, so cold, leading to displace the warmer air higher up at 60 degrees north, and we get this nice circulation of air here. The Hadley cells we talked about, rising air at the ITCZ, at the equator, sinking at the tropics of Cancer and tropics of Capricorn, and then these would be ferrule cells here, where the air is basically between 30 and 60, rotating to kind of fill the void on the opposite sides between those two major cells. So it's not just the fact that the Earth has air that's warming, but we know that the Earth is spinning, otherwise half the Earth would have burned and half the Earth would have been frozen. But as it's spinning and as it's rotating, it's actually spinning, in this little physics lesson for you, at different speeds. Now, that might not sound great, but it's actually moving much faster at the equator than it is at the polar regions, basically meaning that it's covering more distance. So the Earth itself, since it's covering more distance, is technically going faster. And since it's going faster at the middle and slower at the top and at the bottom, it actually creates a deflection because there is a change in speed. That deflection is what we call the Coriolis effect. So because the Earth is rotating at the North Pole, if we were to just roll something, we would think that on a flat surface it would go straight. But since that thing is spinning, as we get further away from the center, it's actually going to deflect in a specific direction because the Earth itself is rotating. Now, that deflection happens if you're going up or down, and we can look at it from the Tropic of Cancer, Tropic of Capricorn, 30 north and 30 south. We can see exactly, because the Earth is spinning in a counterclockwise direction, we see exactly what's going to happen with that spin. So because the Earth is spinning, if I go to throw it, that ball is going to deflect to the right from 30 north, or deflect towards the equator and to the left, 30 south. 30 north, going in this direction. At 30 south, it deflects in this direction, and going from 30 south this direction. So we see that there is some deflection because the Earth is spinning. That's our Coriolis effect. Now, why is that important? Well, we talked about rotating air here, rotating patterns of air. Now we're talking about spinning. So what happens to those rotating patterns of air is we actually get what are called prevailing winds. And your prevailing winds are basically the combination, the result of those Hadley cells, those convection currents, those polar cells, and the Coriolis effect. So because all this air is moving and all this air is spinning at the same time, we see, and the Earth itself is spinning underneath it, those things are actually moving based on that Coriolis effect, that deflection. So we see that in our area we have what are called westerlies, because the winds begin in the west because of where the Earth is and because of the air itself actually moving in this direction. It's, in our area, it's rising up like this. We see that's going in this almost clockwise direction. And because it's spinning where it's spinning, that wind itself is actually moving across us. And we see that's why our jet stream and our weather actually moves from the west coast to the east coast. So we know what our weather looks like when it starts out over the western part of the United States. It is important to know which direction the wind blows in each of these sections. So the wind blows to the east here, west between the 30s, and then it blows east closer to the poles. So east by the poles, west and west. Now remember that the names of winds are based off of where they originate, not the direction they are blowing. So we have westerlies that blow east, and we have the northeast and southeast trade winds, which actually blow west. So just keep that in mind. What's the last thing that results in climate? Well, we know we have seasons in certain parts of the world, and that has to do with the Earth's tilt. So in the northern hemisphere, when we're tilted towards the sun, the southern hemisphere is tilted away and vice versa. That's why we have our opposite seasons. The further north and further south you get, closer you are to the equator, tilt matters less, and that's why they have a very constant temperature, constant climate year-round. They don't really have seasons closer towards the equator. So if you're closer to the equator, it doesn't matter which direction you're tilted, you're still getting a pretty good amount of sunlight no matter what part of the year you're in. However, depending on that tilt, you look at it on this side, over here, our December solstice, the northern hemisphere is getting much less light compared to the southern hemisphere. That light is hitting the southern hemisphere directly, just like in the June solstice during our summer, that sunlight hits the Earth directly in the northern hemisphere and less in the southern. That's why June is our summer and their winter, and December is our winter and their summer. So we know that the air is getting warmed, but the other thing getting warmed is also the water, because obviously we said the sun's energy can be absorbed by the water. So just because the air is moving creates those convection currents of air, warming water is going to cause ocean currents. Now it's not just warming water, it's also has to deal with gravity, the Coriolis effect, but basically since warm water rises and expands, cooler water is going to condense and sink, we get water circulation. Now we call these things gyres, and they're basically, what we know about our Earth is that there are just large-scale circulation patterns because of all these climate factors of where water rotates in the Earth. Now we do know that because of rotation, that the water does rotate clockwise in the northern hemisphere, these gyres, and counterclockwise in the southern hemisphere. So because water is rising and sinking because of different densities and different temperatures, this results in a process called upwelling. Now upwelling is important in different climates because when water cools and it drops down, it displaces water near the bottom of the ocean floor. And because of those thermal vents down at the bottom of the ocean floor that are pumping in a ton of nutrients, that water is then able to rise. So upwelling is very important to providing nutrients to many different ocean populations. And because those support a large number of producers in the ocean, algae and things like that, their support, that nutrient movement, very important in terms of providing the producers that are needed to support the fish and the fish life there, which in turn supply the mammals and could affect our own fishing industry as well. So because we have water moving, we call this whole process of where all this upwelling occurs, mixed with all, combined with the fact that the water is moving up and down from the surface down to the deep water, we call this our thermohaline circulation, basically water and salt. Now, this process is very crucial, we were saying, because it does not only move nutrients, but also moves heat around, which regulates climate and regulates ocean temperatures. And if we start to mess with ocean temperature, we start to see it changing different climates, because that water can affect not just the water temperatures, but can also affect the climates of the land masses that are nearby. So here we see all of our thermohaline zones, and you can see we're talking about clockwise in the north. I'm sorry. Yes, I'm sorry, I said that wrong before. Water goes clockwise in the northern hemisphere in these currents and counterclockwise in the southern hemisphere. And here we see that clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. These dark gray areas are areas of upwelling, basically where that warmer water and that cooler water are mixing is going to lead to that nutrient rise and that nutrient basically flow, which is going to get spread out as that water is carried across the ocean. So here's just giving you a little bit more explanation of the thermohaline circulation in our area, talking about colder salty water sinking, mixing with deeper ocean water, and basically this process drives ocean currents. So this process of moving up and down where the warmer water rises and the cooler water sinks. Now, as that warmer water is rising, especially as it's moving towards the poles down here, up here, we see it's going to start to lose some water to evaporation. Some of it's going to start to freeze, so it does become a lot saltier and a lot thicker. That saltier, thicker water definitely leads to sinking and mixing with deeper ocean water as it moves. And these processes basically drive the cold current that moves past Antarctica, basically results in this large, massive transportation of heat, because now we just have this cold water moving along the bottom of the ocean floor and this warm water moving along the top. So ocean currents can definitely affect temperature of nearby land masses. For example, if we go back for a second, we see England here on a basically direct parallel with Newfoundland, Canada. And you say, okay, direct parallel should be very similar temperatures from all the other stuff we've been mentioning. But what actually happens is that England's average winter temperature is much warmer than it is on the same latitude in Canada, because warmer water is passing by England, whereas by Newfoundland, Canada, it's part of the colder cycle of water coming down from the poles. The warmer water that's rising up towards the Arctic moves past England, which results in warmer average temperatures up there, warmer climate in the winter, as opposed to the cooler water moving past Newfoundland, Canada, as it moves down the Atlantic, which results in much colder temperatures despite being on the same latitude. So here we see basically the large ocean currents, and we see the large flow. So we can see that where the water is basically in certain parts of the world, where that colder water starts to rise as it's warming, as it's moving from the poles, and basically becoming much warmer water, happens in our Indian Ocean, happens in the Pacific Ocean, and then that shallow, warmer water makes its way past the Americas and rises up, of course, past Europe, where it's going to cool again. And this is basically that process of upwelling and that circulation of warmer and cooler water. This is basically what ocean currents look like. We have a warm current that's very shallow and a very deep cold current. And this is definitely responsible for climates and specifically some of the biomes we're going to talk about in different areas. So you may have heard this term before, and it's important to bring up because it is definitely responsible for certain storms, but you may have heard of the El Nino, but what we're going to technically call it is the El Nino Southern Oscillation, or ENSO. So every couple of years, for what's still considered an unknown reason, the trade winds that blow, the southeast trade winds in the southern hemisphere, basically stop, almost to the point they weaken and almost reverse direction. Well, normally, right around that South America, we have deep water that and we have this upwelling towards the surface, which is very important for bringing nutrients and for as far as our temperature goes. Well, when the wind is blowing this way, you see that it also affects the flow of water in that area, and we actually get a reverse of current, and we actually prevents that upwelling. So not only is that going to lead to a change in, we don't have that colder water rising and displacing warmer water, we don't have that nutrients rising, but what we end up getting is a lot more moisture being built up. And since we have a direction, it does have a direct impact on what's happening in the climates of that range. El Nino years basically can have damaging effects on as far as rain production. Some of these winds are responsible for bringing large amounts of rain to different countries, croplands, and without that wind blowing the right direction, it can have a devastating effect on crops. There's also things called La Nina, which are basically the opposite of the El Ninos. We'll talk about those a little bit more in class as well. But basically, this is a summary of our El Nino Southern Oscillation, or ENSO. Basically, that warmer water and air suppresses upwelling, and that does have is going to basically reduce primary productivity. It's going to basically have an effect on the fish populations in that area, and can have larger stretching effects because those winds and that warm water is not blowing in the right direction. What else affects climate? Well, because we have these prevailing winds, because we have off the ocean. Now, here's the first time we're talking about land masses that can affect specific climate areas. And what we have, one of the last things we're going to talk about is a rain shadow. So when we have wind carrying water off of the shore, it will carry water until it basically loses enough energy. But what happens if it hits a mountain range? And you can think of the Colorado Rockies as a good example for this. So as that rain starts to rise up, the air cools, it's going to condense, and it's basically going to start precipitating because it's going to get heavier, and that water is going to fall. Well, the air itself keeps moving, so that colder air basically makes it over the hump, but the water doesn't. And you can see it leads to two very, very different landscapes. Think of this like the northern part of California, your wine country, and over here you have Colorado, which is a lot of flat, dry land, Wyoming, those areas. So what you see here is the fact that all this water is flowing allows for this lush green vegetation to grow in certain areas. And on the opposite side of the mountain, which we call the leeward side, this is called the windward side because this is where the wind is coming from, leads to a much drier, fairly temperature regulated area, but still much drier, not a lot of precipitation. We lead to more, basically leads to a more deserted area as opposed to a more lush greener forested area. And here's basically a summary of your rain shadows that you can copy down, reiterating everything I said. That large amount of water vapor hits a mountain range, and the water can't climb the same way the air is. The water is just physically heavier, so it condenses, starts to drop down, and then that warmer, dry air basically falls over, and that's what we call a rain shadow. So for the Rockies, the windward side, the west side, the rain shadow is the leeward side, the east side. And you can look at wind patterns in different regions to figure out which side of a mountain range would be the windward side and the leeward side. All right, so this is where we're going to stop today. Now, next week we'll go over the specific climates, causes of climate, and look at some of the effects that climate can have on different areas. And then the following week we'll talk about specific biomes. Basically, what are the specific patterns and what are the specific characteristics of these different areas that result from all of this different climate processes. So what are the different areas and what are they characterized by? What are we really going to focus on? That'll be when we talk about terrestrial and ocean biomes, the second half of this lecture. So that's it for our class today. I will see you all after the weekend. Enjoy and have a nice weekend.